Hello everyone. Today we are beginning our exploration of electromotive force, often abbreviating as EMF. This is a fundamental concept in understanding how electric circuits work, and it plays a crucial role in how devices convert various forms of energy into electrical energy. Let's start with the definition. Electromotive force, or EMF, is the energy provided by a source per unit charge that drives electric current around the circuit. Despite its name, it's not actually a force, but a potential difference measured in volts. EMF can be thought of as the push that moves charges through the circuit. As mentioned, the unit for EMF is the volt, where 1 volt equals 1 joule per coulomb. Mathematically, we can express the EMF as EMF is equals to energy over charge, epsilon, which is the symbol we use for EMF is W divided by Q, where W is the energy measured in joules in an SI system, and Q is the charge measured in coulomb in SI units. Imagine water flowing through a pipe. The EMF is like the water pump that creates the pressure difference, pushing water through the pipe. Without it, the water, or electrical charges in this case, wouldn't move. A common source of EMF is a battery. Inside a battery, chemical reactions create a potential difference between the terminals, causing electrons to flow when the circuit is completed, is closed. The chemical energy is converted into electrical energy. Another source of EMF is the electromagnetic induction. This is how power is generated in power plants when a conductor moves through a magnetic field. It induces a potential difference, EMF, across the conductor. This process is governed by Faraday's law, which we will discuss in detail soon. Other examples include solar cells, thermocouples, and fuel cells. Each of these sources converts energy forms from light, heat, chemical energy into electrical energy. Consider a simple circuit comprising of a battery, a resistor, which we will treat as a load, and connecting wires. We can represent this setup with the circuit diagram here. The battery is symbolized by 2 parallel lines, where the longer one indicates the positive terminal and the lower one is the negative terminal. The EMF epsilon is what drives the current through the circuit. In an ideal world, our sources of EMF would have no internal resistance. They would provide a constant voltage without any energy loss. However, in reality, all sources of EMF have some internal resistance. This internal resistance can limit the amount of current that the source can deliver, and it affects how much energy is actually available to the rest of the circuit. We often represent this internal resistance as a small resistor in series with the source in our circuit diagrams. A real battery, for example, might be labeled as having 1.5 volts of EMF, but if it has an internal resistance, the actual voltage across its terminals might be slightly less, depending on the load. This distinction between ideal and real sources is something we will keep in mind as we study more complex circuits. So this would be the basics of electromotive force, which is the energy per unit charge provided by a source which drives current through a circuit. An EMF can be generated from chemical batteries or electromagnetic induction. To talk more about this soon. And finally, we acknowledge that real sources are not perfect and come with internal resistance that affects their performance. May science be with you.